Okay, in this video we're going to look at why some reactions are exothermic and some reactions are endothermic. And we're going to start with a nice simple example. Hydrogen plus oxygen making water. I imagine that almost all of you have done this reaction before. You've filled up a test tube with hydrogen gas, you've put a flame to it, you get a squeaky pop, energy comes out, and the product, though you won't have seen the product in that particular reaction, water, it's a vapour when we do the squeaky pop test, but that is the product, water. So, is it exo or endothermic? Well, pretty well known that this reaction is quite exothermic. Hydrogen burns, it's an explosive gas, so it gives out lots of energy. The question is, why does it give out lots of energy? And to understand that, we've got to know what's going on to the individual atoms. So let's have a look at the equation in a bit more detail. There's the word equation for this reaction. Hydrogen plus oxygen makes water. Now, as you remember, hydrogen goes around in pairs. Oxygen goes around in pairs. And the formula of water is H2O. Now, at the moment, that equation isn't balanced, so hopefully you know how to do this. There are two oxygens on the left, so there needs to be two oxygens on the right. Water is H2O, we can't change its formula, so if there are two oxygens on the right, there must be two molecules of water formed. If there are two molecules of water formed, there are four hydrogen atoms, two lots of H2, four hydrogens. So we must have to start with two hydrogen molecules, two pairs of hydrogens. And that's important. Hydrogen and oxygen always go round in pairs. Now, to explain what's going on in a bit more detail, let's consider those pairs. I'm going to represent the hydrogen pairs using magnets. Here's a magnet, well, a pair of magnets. They're these long flat ones, and as you can see, when I put them close to each other, they attract. Now, hydrogen is not magnetic, neither is oxygen, but on a tiny scale, it is true that the hydrogen atoms on their own separately will attract each other, and that's why hydrogen always goes around in a pair. Same for oxygen, and I'm going to use these big red magnets to represent oxygen. It likes to go around in a pair. So, to make water, we've seen from the balanced equation, we need two pairs, and here's my next pair of hydrogens, and one pair of oxygens. The question is, when they react, what happens? Well, what happens in this reaction is exactly the same as happens in every single chemical reaction. The first step in any chemical reaction has to be the breaking of bonds. You can't get a reaction to happen unless you first break bonds. That's true of every reaction. It's like the old expression, to make an omelette, you've got to crack eggs. You've got to start by breaking something before you make something. So, here is a pair of magnets representing one of my pairs of hydrogen molecules. I pull it apart. It's now two separate atoms. I'm going to put them down there. While I'm at it, I'll do that with my other pair of hydrogens, pull them apart, and I'll put them down there as two separate atoms. Incidentally, if I just put these near each other, they immediately come back together. I have to put in, these are quite strong magnets, I have to put in energy to pull those magnets apart. Same with the oxygen. Naturally, it wants to stay together. I have to put in energy to separate the two oxygen atoms, in the same way that I have to put energy in to separate two magnets. So the first step in a reaction is to break all the bonds in the chemicals that are reacting, what we call the reactants. Now, if we want to find out whether a reaction is exothermic or endothermic, we need to know how much energy we have to put in to break all those bonds. So, moving that away for a moment, let's remind ourselves of the reaction we're doing. Hydrogen plus oxygen makes H2O. Hydrogen goes around in pairs, as we've said, so I can draw a hydrogen molecule like that. There are two of them, so I'm going to draw two hydrogen molecules. I add them to one pair of oxygens. Now, some of you may remember when you did about bonding that oxygen has a double bond. That's not going to affect our eventual discussion. It just so happens that the bond in oxygen is two pairs of electrons being shared, so it's a double bond. And then we make two molecules of water. So let me draw one, and let me draw another. Now, having drawn out the molecules so that you can see the bonds in them, you've got a better idea of what we're trying to break. What we're trying to break is two hydrogen to hydrogen bonds. There they are, number one and number two. And we're also trying to break one oxygen-oxygen double bond. And meanwhile, when they come back together, we make, let's have a look, 1, 2, 3, 4 bonds, where now hydrogen is bonded to oxygen. You could say oxygen is bonded to hydrogen, doesn't matter which way around you say it. Those 4 bonds are all the same. So, with that in mind, let's get back to our magnets. And they're doing things already. They're already trying to bond to each other. That's fine. That's what they want to do. Okay, here are my magnets. I've split up a pair of hydrogens. I split up, if you remember, my other pair of hydrogens. I pull them apart. Likewise, my oxygen, I pulled it apart. I put energy in to break all those. When oxygen meets hydrogen, you hear a sound. Energy is released. Oxygen and hydrogen are attracted to each other. You hear another sound. When another bond forms, you get more energy released. So this model now represents a water molecule. Do the same with the other one. And we've got two molecules of water, where O is the red and hydrogen is the black. Okay? The important thing about that is they want to bond together. So, when they come near each other, they bond and they give out energy. We can tell they give out energy. We can hear it. We see the hydrogen move. It gains kinetic energy. It makes a sound. Energy has been given out to the surroundings. So, breaking bonds, if you remember, I had to put energy in to pull things apart. Making bonds, I get energy out. And that's really important. So important that we better make a permanent note of that. Breaking bonds, which is what you do at the start, equals endothermic. Remember, endo is like entrance. It's what goes in, whereas making bonds, you get energy out. It's exothermic. And energy out, you think of the word exit, exothermic. Exo, out. Thermic means heat. Endo, entrance, heat. Okay? So, key point then, to put energy in to break bonds and getting energy out when you're making bonds. So, how do we know then this reaction is exothermic? Well, of course we can do it and it goes bang, or we can calculate how much energy we need to put in and how much energy we get out. If we go back to our counting of all the different reactions, 2 hydrogen bonds and 1 oxygen-oxygen double bond need to be broken. 4 hydrogen-oxygen bonds need to be made. Well, the strengths of these bonds have been measured by scientists very cleverly, very carefully. And these strengths can be found out by going on the internet or looking up in a fascinating book like the Chemistry Data Book. and I turn to the right page, and you might just be able to see there, it says average bond enthalpies. Enthalpy just means the energy stored within something. So the average bond enthalpies, it's the amount of energy you need to break the bond. Now, to break one bond, you hardly need any energy. It's a tiny amount. So we measure it for a whole mole of bonds. And you might remember that a mole is 6 times 10 to the power 23. It's an awful lot of bonds. And the amount of energy we need to break these bonds, well, it's different for every type of bond. For example, the bond energies I have just looked up, well, the HH bond takes 436 kilojoules per mole of bonds to break. The oxygen double bond takes 498 kilojoules to break. And the OH or HO bond takes 463 kilojoules to break a mole of it. But we're not breaking a mole of that, we're making a mole of that. So that energy is going to be coming out rather than going in. That energy has been going in because we're breaking HH bonds. That energy is going to go in, endothermic, because we're breaking those bonds. We're making those bonds, so we're going to get that energy out. Now, to get our calculation correct, we need to remember how many bonds we're making and breaking. And at the top, you see I said we're breaking 2 HH bonds. So we're breaking 2 lots of bonds that take 436 kilojoules to break. We're also breaking 1 lot of oxygen-oxygen double bonds here, and they take 498 kilojoules of energy. And those are all the bonds we break, and that's the energy we're putting in, the endothermic part. What about bonds we're making? As you see at the top, we're making 4 HO bonds. 4 bonds that, if we were breaking them, would take 463 kilojoules. Now, we have to do a bit of maths to work out how much energy we're putting in and how much energy we're putting out. These bonds are being made, so it's energy out. 4 times 463. I'm going to leave that calculation to last, actually. I'm going to do this calculation first. 436 doubled is 872, 880, 970. That is 1,370 kilojoules in. That is to break bonds. That is the energy we have to put in. The energy we get out is 4 times 463. 4 3s are 12. 4 6s are 24 plus 1, 25. 4 4s are 16. We get 1852 kilojoules of energy out. To work out the overall energy or enthalpy change, we do the obvious thing. Enthalpy change, which you may remember has the symbol delta H, is equal to what you do first, the energy you put in to break bonds minus the energy you get out when you make bonds. So in this example, it's the energy you put in to break our hydrogen oxygen, 1370. Take away the energy we got out when we made 4 OH bonds in water, 1852. You do that calculation and you get an answer of, I've got to think about that one now. It looks to me like it's 482 kilojoules per mole. Minus, because we got more energy out, so that number is bigger than that number. Minus. And if your final answer is minus, that tells you that your reaction is exothermic. A minus answer, or a negative answer, equals exothermic. Think about this. We put in a small amount of energy to break bonds than we got out making bonds. So overall we got more out than we put in, so it's exothermic. And of course it is. Hydrogen burning in oxygen. It's a very exothermic reaction. It goes squeaky pop. If you don't believe me, watch that clip of the Hindenburg airship blowing up when it's landing at New York airport. Okay, so that is a quick run through on how we work out if a reaction is exothermic or endothermic.